try to get an example in because it's the end of the day and nobody can really focus unless we're doing something. So first I'm going to tell you more about transverse knots, and this is where all the questions from last time about braids and stuff comes up. So here are my top facts about working with transverse knots. And so if you're going to actually work with transverse knots, you really should know these. You should know that you can use these. So first thing is due to Bedekin in 1983. If you have a transverse link, T for transverse, inside my contacts manifold from the last talk, this can always be realized as braided about the braid axis of your rotationally symmetric contact structure. So this is the X3 axis. So remember, this rotationally symmetric one was the contact planes here, boop, 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 and then everywhere else they kind of start tilting, and then in infinity they're quite flat this way. So there's this. Some people are smiling back there. But anyways, this is always true.
Realize meaning transversely homotop to such a guy, right?
Yeah, you can transversely isotope any transverse link in here and get it to be braided. So that actually tells you the other direction. You can, this actually is the set. Well, this has been actually improved. Clearly some of these are going to be the same, right? Well, maybe not clearly. If you close up two different braids, it's likely you're going to get the same. It's possible that you can get the same transverse knot type. So recently, we actually know more about this. Orevkov, Shevchishin in 2001, and Wrinkle in 2002. They showed what's actually what I'm going to call the transverse Markov theorem. So just like in the smooth case, we have Reidemeister moves relating all the diagrams for smooth knots. We actually know that transverse links, the set of them, isotopy classes, is equal to the set of braid closures, modulo something, modulo, well, there's braid isotopy. I don't know if I really need to braid conjugation, maybe I shouldn't, yeah. And then only positive stabilization or destabilization. So maybe braid isotopy and conjugation is just kind of clear, because if you have a closure of a braid, if you conjugate it, then you can move it all to the other side and Reidemeister to it all the way. The surprising thing is all you need is this plus positive destabilization. So this is why when I say transverse stabilization, I mean negative stabilization. Because positive preserves your transverse knot type, but negative does not. It actually decreases your self-linking number by 2. Okay. Right, so I'm just going to draw a picture of positive stabilization. So here's my Lagrangian projection of my braid. Here's B over here. And then if I stabilize, I'm adding a positive crossing here. Okay, so just for some notation, I'm not actually sure if I'm going to use all of these, but I didn't bother to check. B is going to be a braid in the braid group with n strands, so that's the braid index. Ride is W, right? We said it was equal to positive crossings minus negative crossings. Self-linking number is equal to ride minus braid index. Okay, so B hat is the closure. And then if we want to think of B hat as a transverse knot, I'm going to say T so maybe, equal T. And if I want to talk about the smooth isotopy class, it's a K. I might not get to using all of these. So one more type of theorem like this. Where did the eraser go? So this transverse Markov theorem is kind of named after the original Markov theorem, so let me just note that as well, because it's going to be useful when we talk about smooth things. So the original Markov theorem said that actually smooth links is the same as a set of braid closures again, but you're modding out by all those like braid isotopy, conjugation, and then all both positive and negative stabilizations and destabilizations. Okay, so why are these top facts important? I erased the first one, but maybe it's okay. So when, in Lenny's paper, which his talk is based on, if you want to prove an invariant is a transverse invariant and you only have a combinatorial description for it, so you have like no geometry to work with, you can still just focus on the combinatorics because you can just say, by the transverse Markov theorem, if I can prove that my invariant, which is defined on braid closures, is invariant under conjugation and stabilization, or positive stabilization, then it's a transverse invariant. Similarly, as I said, the infinity theory is a smooth invariant. And how does he prove that? Well, because of the Markov theorem, all I have to check about my combinatorial invariant is that it's defined on braid closures, but it's invariant under conjugation and both positive and negative stabilizations. Does that make sense? Okay, so that's all I'm really going to say about the proof. I have until 4:30. Okay. Great. Okay, so that's the first 10 minutes. Let's see. Oh, yeah, another piece of notation, because I'm tired of writing this. R is just going to be the usual coefficient ring for the original knot contact, DGA. Okay, so again, I typed up all this stuff, except I didn't actually type up the definitions of how to define the combinatorial invariant, because you can just look it up, and I'm going to put these up here. Okay, so the only difference between the original in the combinatorial version, the hard part, as Lenny says in his paper, the hard part is not like making this little deformation in all these matrices. The hard part was actually using these theorems and trying to prove invariance under those moves. So I'm just going to show you what the new differentials look like. Okay, so originally we had these like A matrices, and those hat A matrices, just kind of ignore them because in some theories you can set U equals 1 and then that hat goes away. In this case, remember in my previous talk I was saying that intersections of the projections of our holomorphic disks with certain hypersurfaces gave us these like U and V powers. Those are the same U's and V's. So now we're going to work over R joined U and V. First thing we're going to do is define some auxiliary matrices. So this is going to be kind of like you're collecting your generators in a way so that when I is greater than J, it appears in this matrix, and then when I is less than J, it appears here. And remember, for the A and B generators, I cannot equal J. Okay, so with these, you're going to define this, for what I can tell, it's an A from an A2. I don't know if you want to think of it that way. So this, notice it has a U in it, so it kind of corresponds to intersecting with this H plus, and this has a V in it, which kind of corresponds to intersection with A minus. Sorry, with H minus. Okay. if I have time at the end, I might wave my hands wildly about why these appear where they are. But yeah. Okay, so now that we have these two things, there's a couple of other things we have to define. Right, I don't know why I put them in this order, but the B matrices, again, you're recording your generators, but now the generators kind of come with some multiplications with U's and B's and stuff. And then you had this is not so important, well, yeah, it's in the differential. This is kind of more significant when you're thinking about links, because you actually need to record like your components and stuff, but that's what it is. It has this factor now. W is a rise. Okay, so how is my differential changed? First of all, generators have like, there's C plus C copies of them. This, still the same, because differential decreases your grading by 1, so there's no grading 0 thing. B, C, and D are grading 1 generators, and then they map to things with A in it. So differential of B actually doesn't involve anything that's new. And I might wave my hands about that. C and D do have these to and from things, and then E and F have these like B to and from things, which also have some sort of U or V in it. Okay, so...
The observation is if you set B equals 1 and forget that I changed convention somewhere in the middle, that's the same as what Ursula wrote.
Right, and this hasn't been very clear because I didn't write this one out. If I had written out, or if you like tried it out and you wrote this out, you would basically get, okay, you would get this matrix with like, maybe there's like a U there, ignore that U, not the same U, but maybe, okay. And then there's some,
No, it's okay.
okay.
I think it's okay.
And then there's some V's in here.
This mu was replaced by
no.
mu inverse somewhere, so
Yeah.
that's why
But that is that a hat.
that there's an A hat here, and that's the same as that A hat. The A check over there is A over here.
Yes.
Okay. Okay, yes. So A check is going to have some like V's because check looks like a V. That's how I remember it. Okay. So there's going to be some V's in here, some U's in here, but if you set the U's and V's to 1, you actually get the original theory of not contact DGA. So it's like an enhancement. It's a deformation of sorts. So before I go on, let's do an example. Even though it's a very simple example, it's always useful to kind of see like what should I be plugging in where. And I think I might not write down everything in the example. Okay. I bet you can guess which example I'm going to do. Here's my braid axis. That's my braid. It is the unique braid in the braid group of, index 1 braid. Okay, so this is, in the transverse world, known as the self-linking equals -1 unknot. And I can actually say this because the unknot is transversely simple. So this is technically a complete invariant of unknots. I don't know. So let's just record that the rise, okay, it's the number of positive crossings minus the number of negative crossings, so that's 0. Okay, and then braid index is 1, so you can check that that's true. Okay, so what is our algebra from the original, I guess, the combinatorial talks? So remember, what we really want is some braid representation. We're supposed to have this function. Maybe I want to call that some algebra. Right? It's really degenerate. So we're supposed to be able to take some braid here, and map it to automorphisms. Um, yes,
A1.
I don't want to mess this up. Okay. DGA. Okay. In any case, there's only one here, so this must map to identity because of rings and stuff. So that means that our algebra is actually just like, I mean, our action is just identity. Okay, so this tells us that phi sub b, which is just that, is equal to identity. So that tells us that all of our big phi matrices, L and R, they're just going to be -1, I think. Lambda. I didn't write them here. Okay, so, okay. If you remember back to Ursula's talk, there's this kind of phi thing, and then she defined these things, and she said those were like kind of like square roots of this thing. Yeah, so all it is basically you have this automorphism, let's try to find a matrix way to write it down. So maybe if we just conjugate, like with this on the left, or not necessarily conjugate, you can write down and find these invertible matrices that kind of give you how to compute this in terms of the basis that you chose. Yeah, I for some reason thought it'd be written up somewhere, but these are going to be -1. This is the 1-by-1 matrix -1.
They're really -1 and not +1?
I think so. No, it's 1. Thank you. Wow.
I mean, I think the action is not trivial, so yeah, there shouldn't be any minus signs coming in.
Yeah, that's probably good intuition. Oh, that's what I'm thinking of as -1. Okay. Okay, so there are no AIJs. There are no BIJs. And that's because I need to be different. So there's really only 4 generators. Since n equals 1, there's going to be C11, D11, E11, F11. So I'm just going to call them, the generators are C, D, E, and F. And these are the same from Antoine's talk because they're supposed to correspond to these like longer chords that that you really see from the unknot. And since we're literally doing the unknot, these are actually the same things. Okay. So we also need this to and from or hat and check matrices. So this is the one that's equal to -1. And how do I know this? There are none of these. 1-by-1 upper triangular matrix. Okay, yeah. I don't even need to write the matrices here. I think you guys know what I'm talking about. So that tells me that this is equal to -1 minus mu times u times -1 by that formula. And at this point, I guess you guys can probably see what I'm doing. I'm just plugging in things to here. Okay. So I'm not even going to have to write down very much. Okay. So this is equal to -v minus mu. The other thing we know is that lambda b, bold lambda b, is, okay, so it's lambda times mu to the right. The right is 0, so it's just lambda. This thing I put here so that if you're trying to compute the infinity theory, there's this funny thing where you're computing using like, instead of, this is not important, but instead of using like h1 in your coefficients, you like instead use h2, and then self-linking stuff comes in because of this, like comparing twisting of 2 bundles and stuff, but it's essentially the same. Okay, so maybe let's compute just like one differential together. So del minus of C, the formula is A hat minus lambda B times phi L B times A check. Alright, so I'm just going to plug it in. You have all this stuff. This is equal to, you do some manipulations and you get, well, okay, let's just write this out. This is from here, minus lambda times, it's very trivial, minus V minus V. Okay, so this is, you guys can all do this, right? Is anyone confused about where I'm getting anything from? I guess that's the whole point of this. Okay. Yes, so you can keep computing all these differentials and it fits on a page with really big handwriting. So as Antoine said, if you're clever, you can figure out that up to stable tame isomorphism, you can actually get rid of two of these generators. But if I'm not so clever, that's okay, because remember how I told you that there are all of these invariants, and some of them are easier to compute than others. Okay, so let me leave that for differentials later. So let me seriously talk about the flavors now. So last time I said you can have minus, hat, double hat, etc. So let's do, this is K, C, A minus. This is K, C, A hat, K, C, A double hat, K, C, A, the original, and K, C, A infinity. So for most of these, you can just set U equal something and then you actually get it. So this is the original, you just have U's and V's. These two are going to be over just R, or really all three of these. This is U, V equals 0, 1, or isomorphically 1, 0. Yeah, okay. And then this is probably 0, 0. Yes, 0, 0. This is 1, 1. So setting U and V equal to 1, you get back to the original not contact DGA. And this is the whole like tensor with stuff, and then like lambda gets sent to some other stuff. So these three are transverse invariants, and then these two are smooth invariants. And at the beginning of this talk, we talked about how to prove that on a grand scheme. Okay, so let me just finish talking about, just writing down what these differentials are. Really not too many of them. So here's C. I've computed here that del minus D is equal to negative lambda inverse V lambda. I don't know if to say this out loud. Doing the same thing as I did here. And then, you know, there's two others that I'm not going to write out. So let's say that I am not clever enough to actually figure out how to do cancel out two generators, these two, and I just want to compute invariant right now. Well, I can choose one of these, right? I can just plug things in and then things get a lot easier. So I'm going to choose, let's say, the hat version, and I'll just compute it. So I want to set U equal to 0 and V equal to 1. Furthermore, so let's compute KCA hat of our closure of the one identity braid as a transverse knot. This is a simplification, but also remember how I can just take the degree 0 part, and that's already an invariant. Is everyone okay with that?
You mean the homology or what?
So it's
Yeah, I do.
en mode
Yeah, because I'm actually going to be computing homology. Yeah. Right, so in the original not contact homology, that was the part that's isomorphic to the chord algebra. So with these two simplifications, I can literally write down, well, my generators in degree 0 are A's and B's. There are none of them. So since I'm working over R adjoined UV, all I have is R adjoined UV, the coefficient ring. And I'm modding out by all of the images that are hitting degree 0. So that's going to be images of things that are degree 1. And so that was B, C, and D. But since there are no B's, I'm just looking at the images of C's and D's. But this depends on that, right? It's just a like times lambda inverse something. So this happens to be like commutative, so two-sided ideal, whatever you want to call it, minus 1 minus mu times 0 minus lambda times, well, plus lambda times 1 plus lambda mu. Oh, y. So u equals 0, v equals 1. And
So it's R mod, that ideal.
Yeah.
it's R adjoined, oh sorry, yeah, sorry.
Yeah, U and V.
I'm in the hat version. Yes. Yeah, sorry. In the hat version, it's definitely just R. And this is something that I guess like you can understand.
And so what happens if you do a negative stabilization? I mean a positive stabilization?
Oh, right. So if you get a positive stabilization, you get bigger matrices and stuff.
Yeah. Okay.
So then this is actually the degree 0 part of the positive stabilization, so not the transverse stabilization, still the same knot, is shown in Lenny's paper. And you can compute that. But the entire thing is harder to compute because your matrices are bigger. But a computer could definitely do it. Okay, so I have about 1 minute left for hand waving.
Actually, let me ask you a question first. What happens with the negative stabilization over the constant
yeah.
stabilization?
I thought about working this out, and then I didn't think it would fit in a 30-minute talk. So, I don't know if I can say anything about that yet.
So, yeah, the hat
That's your
version,
friend.
it's a little bit weird, but the double hat version under transverse stabilization, it actually vanishes. So you get the invariant, the entire invariant just vanishes. D if something is equal to 1.
Okay. I'm going to wave my hands for 30 seconds. So how they actually prove, or how did Lenny, how did Lenny and his collaborators show that this transverse combinatorial version is actually the same as the geometric one? I don't know, but here's my idea of how they did it, which I also wrote hand-wavingly in the notes. So as Antoine said, right, you have these big rate chords corresponding to like these that come from the unknot. And again, you're doing this thing where you're they show that geometrically you can shrink any sort of braid closure really, really, really close to this unknot. So then basically you get like big rib chords and small ones. And then you basically show that the small ones can't really intersect with your H plus and H minus. Maybe because they're too small, I don't know. I can't really check it at this point. But that is why you see that, remember that the A and B generators are coming from tiny chords. Right, so that's why the differentials for them don't actually involve any U's and B's. Whereas these long chords might actually intersect things. Yeah. That's all I have to say. Any questions for Melissa? Yeah.
What does it mean? What does it mean? You know, when you set to the u equals to 0, like what does the quantity mean?
I don't think I have Lenny would probably give you a more intuitive answer. To me, it's just like this is a deformation, and I'm setting, I'm collapsing it somehow, but
You're
I don't
forbidden
know.
disks to go through one of the two.
Oh, yeah, okay. Yes, so remember in the differential, we had these u times whatever. So if you set u equals 0, then you're not counting the differentials that involve disks that intersect the positive hypersurface. Yeah, and same with setting v equal to 0. Thank you. Did
This
you
is
have a
inspired by Hegel-Floer, where something similar happens.
question? Yes.
You take the half version of various theories, and you're restricting the number of holomorphic disks you got.
I forgot to mention, in Hager-Floer theory, the base points that kind of puncture your disk that you don't count have actual grading. In here, u and v have nothing to do with the DGA grading. It's just 0. So, did you have a question?
Yeah. Is there any way of defining invariance from the filtration, like tau or similar things? Or you look
Yeah, I really want to see this happen.
or something from spectral sequences converging somewhere.
I haven't found anything about this because I was also wondering this.
Would be
So,
cool.
yes. Get some concordance invariance somehow, or
Somebody did
symplectic concordance, yeah.
Okay, let's thank Melissa again.